All right, it's 9:20. It's time to get started. So for the folks wondering about the recording from last Wednesday, it's actually up on YouTube now. So there's a YouTube playlist linked from, if you're in the course, it's linked from the announcements channel. And if you're watching on Twitch, it's on my Twitch page. All right. Um, so today we're going to pick up where we left off last time. Last time we started to talk about delivery properties. So the first one that we started talking about was FIFO delivery, and we just barely managed to start talking about it before we had to wrap up. But today we're going to talk about it a lot more. So let's come back to that. So first of all, let's recap the difference between receiving and delivery, because that's something that can be confusing. I found this confusing when I was new to distributed systems too. So, so sending a message is something you do. Receiving a message is something that happens to you. But delivering a message is something you do. So if you want to, you can think about when a message is received. Let's say that we have processes A and B here, and A sends B a message. You can think about there being a little mail clerk hanging out here on process B who sees that a message has been received and who makes a decision about whether or not that message should be delivered on process B. And delivery means that the message is now available to look at on process B. So messages could be received on process B, but then they could actually be queued up for later delivery, or they could be delivered right away, depending on the application and the needs of the application. So the difference between receiving and delivery is that receiving is just something that happens, and you can't control when it happens. But delivering is something that you can do with a message that you receive, and a protocol can wait to deliver a received message until the right time. And this is actually a really important mechanism. Why might you want to queue up a message and not read it yet? Sure, maybe you're working on other things. Ordering, yeah, that's a good one. So a message might have been received out of order. So that brings us back to, so what I wanted to talk about first today was to talk about FIFO delivery again. So FIFO delivery, and here's the definition of it again, repeating what we had last time. If a process sends message M2 after message M1, then any process delivering both delivers M1 first. And we said a violation of FIFO delivery would be something that looks like this. So here there's two processes involved. Process one is sending two messages. You could call this M1 and this one M2. And we're seeing here that these messages, we haven't written delivery explicitly in this figure, but we're assuming that these messages got delivered when they were received. And if so, then this would be a FIFO violation. And FIFO, of course, stands for first in, first out. So you could think of there as being a sort of pipe between processes, or a channel, as we're going to call it later. And a FIFO violation would be a violation of the order of messages in that pipe. So a question being asked in chat right now is, how would process 2 know that there's a problem here if it never receives M1? So that's why this delivering both is part of the definition of FIFO delivery. So if it never actually receives both, right, then it's not a violation of FIFO delivery, because it can't deliver both unless it receives both. So if it doesn't deliver both, then the premise of this if hasn't been satisfied, and so the property isn't violated. Okay, so this is why the ability to queue up a message and not deliver it immediately is important for enforcing things like FIFO delivery. So as a distributed systems implementer, though, you actually won't have to implement FIFO delivery yourself very often. So why is that? Does anyone know? Yeah, TCP is what people are mentioning. Yeah, it's already part of TCP. So most distributed systems communicate over TCP, probably. TCP already enforces FIFO delivery. So if you need FIFO delivery, it might be a good idea to use TCP. Okay, so that's FIFO delivery. That's kind of one of the most basic kinds of delivery guarantees that we're going to talk about. What about causal delivery? What does that mean? So it's going to be something like, if M1's send happens before M2's send, then M1's delivery happens before M2's delivery. There are different ways of phrasing this one, but that's a phrasing that makes sense to me. So going back to that FIFO anomaly, or actually I can just draw it again here. So we know this is a violation of FIFO delivery. Is it also a violation of causal delivery? Yeah, I would say yes. Because we know, right, from the definition of happens before, that if this event is before this event on the process line, then this event back here is in the causal history of this one, right? So if we want to call these events here A and B on this first process, P1, then A is in the causal history of B. So if we come over here and this message gets delivered, then that delivery is happening too early. So really this message, the message whose send was event A, should have been delivered before B in order for causal delivery to hold. So our violation of FIFO delivery is also a causal delivery violation. Let's go back to our Bob Smells example. So we had Alice sending a message that said Bob smells. And Bob was sending his message in response, F you. Carol is confused. What kind of anomaly is this? Is it a FIFO violation? It's not a FIFO violation. Why not? Well, my favorite word that I couldn't remember last time, remember vacuous? So vacuously, this is not a FIFO violation because remember the definition of a FIFO delivery, right, is if a process sends message M2 after message M1, then any process delivering both delivers M1 first. So the same process has to be sending those two messages to the same receiving process, right, for it to be a FIFO violation. And that's what's happening here. We have one process sending two messages to the same receiving process, and they're showing up in the wrong order. But that doesn't actually happen here because there's no process in this picture that receives, let alone delivers, two messages from the same originating process, right? So Alice is sending a message to Bob and a message to Carol. Bob is sending a message to Alice and a message to Carol. But there's no place in this picture where there's one process that's sending two messages to the same receiving process. So vacuously, this is not a definition, this is not a violation of causal delivery. So this one is not a FIFO delivery violation, but a causal delivery violation. So FIFO delivery by itself, if all you have is a system that enforces FIFO delivery, that will not by itself prevent this kind of problem from happening. It's a causal anomaly. All the interesting causal anomalies like this one require 3 or more processes to demonstrate. So there's a good question in chat, which is, can a message go to multiple destinations? So that's kind of what's happening here, right? Like this message from Alice is getting sent to both Bob and Carol, and this message from Bob is getting sent to both Alice and Carol. So we're actually going to talk about that more later. This is what's known as broadcast. When somebody sends a message and it goes to everyone else in the system. So for now, you can think of messages. You can think of, if you want to, you can think of these as being two separate messages that were sent right next to one another. But but yeah, we're going to come back to this topic of broadcast very soon. So here's another correctness property that you might want for message delivery. Totally ordered delivery. If a process delivers message M1, then M2, then all processes delivering both M1 and M2 deliver M1 first. What's an anomaly violating this one? So let's say that we have two processes. I'll call them R1 and R2, and two clients. C1 and C2, who you can also think of as being processes. Let's say that the clients send messages to R1 and R2. And let's just say that these clients are sending writes to a key value store that's replicated across these two processes. So let's say client 1 is writing x equals 1. Say client 2 at the same time is writing x equals 2. Maybe x started out at 0. Folks are complaining about the noise level. I don't know why there's more noise today. Sorry about that. Is it any better now? Okay. Let me know if there's a problem. Okay, so we've got these two clients, right? And they're writing these different values, x1 or x equals 1 and x equals 2 to these two replicas where x is stored. But the updates are getting delivered in opposite orders. So let's say you're replica 1. You get this update from client 1. It says that x is 1. A little while later, you get an update from client 2 that says x is 2. So you end up thinking x is 2. Meanwhile, on replica 2, the opposite happens, right? You get client 2's update that says x is 2, and then a little while later, you get this other one that says x is 1. So two clients are writing different values to two replicas where x is stored. And so the updates end up being delivered in opposite orders. Now the replicas disagree. This is what we call a total order anomaly. So this is a violation of totally ordered delivery because this process, for instance, R1, delivered the message from client 1 and then the message from client 2. So this comes back to that question of broadcast. For the purpose of these definitions of delivery guarantees, you should think of these two messages that client 1 is broadcasting here from this same send. You should think of them as both being the same message, right? So you could think of these both as being M1. And you could think of these both as being M2. So the process here at replica 1 delivered M1, and then it delivered M2, whereas replica 2 delivered M2 and then M1. So this is a violation of totally ordered delivery. And what we can do at this point, now that we've defined all these different kinds of delivery guarantees that a system might want to ensure, is we can try to put these delivery protocols in a hierarchy in terms of what it is that they ensure. So we already figured out that FIFO delivery doesn't give you causal delivery, right? So coming back to our definition of causal delivery here. But on the other hand, if you're ensuring causal delivery, does that give you FIFO delivery? If I have this guarantee, if I say my system gives you causal delivery, do I know I have FIFO delivery for sure then also? Yeah, you do, because violations of FIFO are also violations of causal delivery, right? So if I'm ensuring causal delivery, then there won't be any violations of FIFO delivery either. So we know that's the case. So we can start to put these things in order. So at the bottom, we can have like the guarantee that doesn't really guarantee anything. Call it YOLO. YOLO delivery. One step up from that is FIFO, right? This gives you the guarantees of FIFO delivery. One step up from that is causal. So if you have causal delivery, you have FIFO delivery, and you also have FIFO. If you have causal delivery, you have FIFO delivery for free. YOLO delivery is like the empty delivery guarantee. It means there are no guarantees. So what about the one that I just defined, which was totally ordered delivery? Where does that fit into this picture? Where do you think it goes? Here's a picture of a total order anomaly again, and the definition of totally ordered delivery. So where do you think that fits in? Good, yeah. So it would actually get its own branch. So why? Why is that the case? Well, if we look at our FIFO anomaly, this FIFO anomaly here is actually okay in terms of totally ordered delivery. So this is a violation of FIFO delivery, but it's not a violation of totally ordered delivery. Why not? Well, there's only one process here where two messages are being delivered. So if the rule for totally ordered delivery is all processes delivering both M1 and M2 deliver M1 first. Well, there's only one process delivering both the messages here. So again, this property of totally ordered delivery is vacuously true in this case. So you could have runs that violate FIFO, but don't violate totally ordered delivery. And conversely, total order anomalies aren't necessarily FIFO anomalies. So back to our example here, where we had these two clients and two replicas. Is there anything here that's a FIFO violation? Nope. There's not a case here where the same process sends two messages to the same receiving process. So there's no FIFO violation in this picture either. So our hierarchy of delivery guarantees is actually going to look like this. There's actually going to be a separate branch here for totally ordered delivery. So guaranteeing causal delivery will give you FIFO, the FIFO delivery guarantee for free. But guaranteeing totally ordered delivery doesn't give you either of these things. And likewise, neither of these things guarantee total ordered delivery for you. If you wanted to have both causal delivery and totally ordered delivery, you would have to define some other special delivery guarantee, which would then be at the top of this hierarchy. So what we want to do next is kind of start to talk about implementing these protocols. And so this is going to be the topic of discussion for the next couple of lectures. But today we can get started on talking about at least implementation of FIFO delivery, which also, again, is the one that you won't have to do too often. But let's talk about it. Okay, so somebody's asking, well, what does this hierarchy imply exactly? So before we go on to talk about implementation, let's talk about this a little bit more. So let's give this a name. Hierarchy of delivery guarantees. What does it imply? Well, since we see that causal is higher up than FIFO delivery, we know that if a system guarantees causal delivery, then it also gives you FIFO delivery. Since FIFO is lower down than causal, we know that if the system guarantees FIFO deliveries, we have no guarantees with respect to causal delivery. Maybe the system does give you causal delivery, but the FIFO guarantee by itself doesn't provide that. And then if the system provides totally ordered delivery, well, that's great and useful, but by itself, it doesn't imply that there's either FIFO or causal delivery. So this hierarchy tells you something about what it is that you can expect out of a particular delivery guarantee. It also tells you something about what if you have an anomaly, then what kind of anomaly it counts as, right? So if we have a violation of FIFO, then that's also a violation of causal delivery because FIFO appears below causal in this picture. But if we have a violation of FIFO, it's not necessarily a violation of totally ordered delivery, as we just saw here. Okay. So let's start to talk about how to implement FIFO delivery. Let's say that you wanted to rule out this kind of anomaly. How would you go about it? So here's the definition of FIFO delivery again. If a process sends message M2 after message M1, any process delivering both delivers M1 first. So there's an equivalent way to put that, which we could say messages that come from the same sender are delivered at any process delivering both in the order that they were sent. Okay, suggestions on what to do to implement this. There's already one suggestion in chat, which is sequence numbers. So sequence numbers are a typical approach to implementing FIFO delivery. So with sequence numbers, we say messages get tagged with a sequence number from the sender and a sender ID. And the sender increments its sequence number. After sending. So that's what the sender does. What does the receiver do? Yeah, the receiver wants to keep some sort of queue. So what are the rules for when the receiver actually the receiver actually delivers a message versus queuing it up? Right, so we want to, for every received message, we want to look at its sequence number. And we want to ask, is that sequence number is it the sequence number of the previously delivered message from that sender sorry, SN plus 1. If a received message's sequence number is the sequence number plus 1 of the previously delivered message from that sender, deliver it. Otherwise, queue it. Queue it up for later. So this is one way to implement FIFO delivery. In the way that I've sketched it out here, what are some situations where this would not work? Yeah. What if a message gets lost, right? So let's say this. Let's say we have Alice and Bob. And suppose Alice is sending messages to Bob. And so she's happily sending them and giving them sequence numbers. Maybe this is message 1. Bob gets it. He delivers it. Message 2. Bob receives it and delivers it, and so on. Let's say Alice sends message 3, and then that message gets lost for some reason. Well, message 4 comes along, because Alice doesn't know that that message got lost, right? Message 4 comes along, but Bob can't deliver it, right? Because Bob never delivered message 3. So this one would just get queued. Message 5 would get queued. And so on, right? So these later messages would end up being buffered forever, right? If a message got lost. So this strategy that we just sketched out for FIFO delivery, here it is again. This only works if you also have reliable delivery of messages. So we'll talk more about reliable delivery later. But this is an approach that would only work, assumes reliable delivery. So somebody asked about these sequence numbers. So when you send a message, so sequence numbers don't necessarily have to be globally unique, right? Because we were saying that when these messages get sent, they also come with the sender ID. So the combination of the sender ID and the sequence number ought to be globally unique, right? But everybody should be able to use the same numbers as their sequence numbers here. All right, so that's one way of implementing FIFO delivery. It's not necessarily the only way. What's another way that we could implement FIFO delivery other than sequence numbers? Actually, before we talk about that, let's, for the sake of argument, let's just talk about, suppose you didn't have reliable delivery. How would you implement FIFO delivery? Well, one thing you could do is you could just go ahead and deliver, like let's say we have this picture here. You could just say, go ahead and deliver any message that has a sequence number larger than the one delivered before, right? So here Bob got a message with sequence number 1 and delivered it, got a message with sequence number 2 and delivered it. A message with sequence number 3 didn't arrive. Then suppose Bob gets this message with sequence number 4. Bob could go ahead and deliver it, right? And the same with 5. But if it turned out that this message 3 wasn't in fact lost and was just delayed, then 3 would come up later, like here maybe. Then under this approach, we would have to just drop that message on Bob's end when it arrived. And you could imagine a system that did that, right? Or you could imagine a system that kind of makes it an intermediate choice, right? And buffers messages, any messages that are received out of order. It might like buffer them for a while. Like maybe in this case, you would buffer up these messages 4 and 5 for a little while, waiting on message 3 to arrive. And then you would deliver 3, 4, and 5 in that order. But you have to pick the buffer size, right? If you only had a buffer that was big enough for one message, then you wouldn't be able to do that. And so this question of buffer size ends up being an important design decision in these kinds of systems. Here's another point to make about this, about FIFO delivery. What if you had this? What if Alice sends a bunch of messages and maybe some of them cross over like this, but Bob doesn't actually deliver any of them? If Bob just drops them all? If that's what happens, is this a violation of FIFO delivery? Or in other words, am I guaranteeing FIFO delivery in this picture? Sure, yeah. So no messages actually get delivered, so it vacuously satisfies that FIFO correctness property. But this is really unsatisfying, isn't it? So no messages are getting delivered at all, so I haven't violated FIFO delivery. And later in the course, we're going to talk about safety properties versus liveness properties, which is relevant to this. Okay, that was a digression. Back to this question about implementing FIFO. So a couple people in chat have already suggested another possibility for implementing FIFO, and as an alternative to sequence numbers. So another way to implement FIFO delivery acknowledgements. So in the acknowledgement approach, we have our sender and our receiver. Alice sends a message, and there's actually no need for her to send a sequence number. And Bob sends back an acknowledgement. Okay, I got it. When Alice gets that acknowledgement back, she knows that it's okay to send another message. And then she waits again to get the okay, I got it acknowledgement. And so on. So Alice won't send her message 2 until she gets the acknowledgement of message 1. So perhaps Alice knows that there's an order to these messages over here, but she doesn't have to send the sequence numbers along with the messages this time. So this doesn't require Alice to send sequence numbers, and it doesn't require Bob to keep track of what sequence number he last saw from Alice, because the work of deciding when to send a message is all taking place on Alice's end. But what's the downside of doing it this way? It's slow. Yeah. So unlike before, when Alice could just fire off messages with sequence numbers and not wait for a response, it's slow. So that's not great. All right. So there are optimizations that you can do, sure. So some people are making suggestions like you could batch up messages and so on. Yeah, so, and that is indeed what real systems do. But there's these fundamental difficulties, right, with implementing FIFO, right? You have to make a choice. You can either do this approach where you wait for acknowledgements and it's slow, or you do the sequence number approach which requires some queuing to be done on the receiving end, possibly, or it requires some bookkeeping, or you could do both, right? And then there's these optimizations that you can do, such as batching messages and so on. But the fundamental difficulty of having to do this and needing reliable delivery in order to make this work is pretty unavoidable. Okay, so that's FIFO delivery. But for the most part, we can think of it as a solved problem, right? If this were a networking class, we could dig really deeply into the internals of TCP and so forth. But this is not a networking class. So let's talk instead about something that's maybe a little bit more interesting, which is causal delivery. So here's, again, what our classic causal anomaly looks like. So the fundamental issue here, right, is that this FU message was delivered on Carol before the Bob Smells message, even though it was causally later. Anybody have a suggestion for how you could prevent that? Hmm. So a suggestion is global sequence number per message. So I'm already a little bit skeptical of that suggestion because of the word global. So I don't know how you would come up with these global sequence numbers. Timestamps. Okay, so we're getting a little bit closer to what I want. But we want them to be logical timestamps, right? Because we don't really have we don't have a mechanism for global timestamps. So the solution that we can actually use to ensure causal delivery in this situation is with vector clocks. We can use vector clocks to rule out this causal anomaly, or any causal anomaly. So we're going to talk about that a little bit more. Let's pause and do a quiz question right now. So here's the link to the quiz in chat. We'll wait a couple more minutes. Okay. So let's come back to this discussion of how we would go about implementing causal delivery using vector clocks, which are the mechanism that we started to talk about before for tracking causality. So before, when we talked about vector clocks, right, we used them to track every event, right? We used them to track message sends, message receives, and so on. So the picture that I showed previously of assigning vector clocks to events in a Lamport diagram, every event counted as an event. In order to implement causal delivery, we can change the way that we use vector clocks slightly. So we're only going to track message sends. And it turns out that that's actually sufficient to ensure causal delivery. So with this caveat that we only have to track message sends, we don't have to consider message receives as events. Let's actually try to attach some vector clocks to the events in this picture, and let's see if we can kind of intuit how vector clocks could be used to prevent this causal anomaly. Okay, so recall from our discussion of vector clocks that everybody starts out with a local vector clock initialized to zeros. So Carol has a local vector clock of 0, 0, 0, and Bob has one of 0, 0, 0, and Alice has one of 0, 0, 0. Okay. Alice sends her BS message. What timestamp does that message have, or what vector clock does that message have attached to it? Right. It should be 1, 0, 0. Because she's now sent one message, right? So she increments her own position in her local clock. The message gets to Bob, whose local clock is at 0, 0, 0. Is this message right here, is it okay for Bob to deliver that message? This first Bob smells message from Alice. Intuitively, yes, right? Because it's the same as his own local clock, except it's higher by 1 in one position. Which position? The position of the process that the message is coming from. So that's okay, right? So Bob can go ahead and deliver that message there. That gets a check mark. Now Bob sends a message. What's the clock on that message? Well, it's going to be 110. So that shows that he's aware of one message sent by Alice, right? This previous one. And he's also aware of this message sent by himself. So that 110 is going to be the vector clock of this event right here. And that vector clock gets attached to the message as it gets sent out. The message gets to Alice. Is it okay for Alice to deliver it at that point? Sure, yeah. Because it's the same as Alice's local clock of 100, except +1 in one position, which again is the position of the process the message is coming from. So that's okay. So it can get delivered there. All right. But is the message from Bob okay for Carol to deliver? This is the key question right here. So the message coming from Bob has this clock of 110. Carol's local clock is 000. So actually, no, it's not okay for Carol to deliver that message because this vector clock of 110 is too big. In particular, the entry for Alice is too big. The message is from Bob, right? So we would expect it to be higher than whatever Carol currently has in her entry for Bob, which is 0. In particular, if it's just one higher than what Carol has currently for Bob, then that's fine, right? But this message with this 110 vector clock on it is also one higher than what Carol has in the Alice position, meaning that it's from the future in some sense. So Carol should not deliver it. She has to buffer it. Then finally, this BS message, right, from Alice gets to Carol. Can she deliver that one? Sure, yeah. So its vector clock is 100. So it's the same as Carol's clock, except that it's +1 in the sender's position. So that's fine. And then at that point, now that we've received this 100 message, now we can go back and look at the one that we buffered, right, which was 110, and we can check if it can be delivered. And it can at this point, because now its clock is the same as the local clock except +1 in the sender's position. So this message here kind of gets delayed until down here where it can get delivered. So it's now okay to deliver now that we've delivered this one. Questions about that? Question in chat is, shouldn't the second event on Bob's process line be 120? So that's where this comes in, where I say we only have to track message sends. So this here actually doesn't count as an event on Bob because it's a receive. So we're only counting sends as events in this algorithm. So you're right. It would have been 120 if this, in fact, if we had been counting message receives as events. And yeah, we're always gonna, whenever we ask you to assign vector clocks or any kind of logical clock to messages, then an important thing to specify in advance then is, well, what counts as an event, right? So in this case, for this picture, we're saying only message sends count as events. In the vector clocks algorithm that I showed earlier, both sends and receives counts as events. And what you choose to do, right, is going to depend on what you're actually trying to accomplish. So here's another question in chat. If Alice only sent Bob smells to Bob, but Bob sent this message F you to both Alice and Carol, would Carol still buffer the message from Bob? Carol would not have received the BS message, right? So then it wouldn't matter, right? Yeah, so in that case, if Alice says Bob smells to Bob, and then Bob decides for some reason to say F you to both Alice and Carol, well, I mean, Bob is choosing to say F you to somebody who wasn't involved, right? So I guess that's Bob's prerogative. But that wouldn't be a causal anomaly. That would just be Bob being a jerk. All right, so there's a question on Twitch chat, which is, does this assume that all sends are broadcasts? Thank you for asking. Absolutely, yeah. So I haven't specified this entire method yet exactly for ensuring causal delivery of messages, but and we'll sketch it out next time. But in the version that I've sort of informally discussed here, this is actually an algorithm for causal broadcast. So the approach that I've sketched out here actually only works if all messages are broadcast messages. Good question. So maybe, I guess we have a couple minutes left, and I don't think it's enough time to actually more formally write down what the protocol is that we're using for causal broadcast. But I want to try to answer one more question from Slack, which was, does Carol's vector clock ever change when receiving a message? If not, why does it stay the same? So yeah, so I hadn't been updating these local clocks here. And we should be updating them, right? So even though message receives don't count as events, we're still following the usual vector clock algorithm, right? Where when we receive a message, it comes with a clock, and then we update our local clock to the maximum, right? So for example here, when Bob sends this message and it has this 100 vector clock, or excuse me, when Alice sends this message and it has this 100 clock attached to it, then Bob's local clock, right, should update to 100 here. And then when this message here gets sent, that's why this one is 110, because he's incrementing his own position. And then when Carol receives this message, this one doesn't get delivered, right? So that one gets queued and that one kind of gets ignored until later. But when this one arrives with the 100, now this position gets updated to 1. And then that's what makes it possible to deliver this other message, which had the 110 timestamp on it, because it gets compared with Carol's local clock. All right. Yeah, and another good point being made in chat is we're also assuming reliable delivery of messages here. So just like our FIFO delivery mechanism assumed, both of the FIFO delivery mechanisms that we talked about, both sequence numbers and acknowledgements, they both assume that message delivery is reliable, right? So there's an assumption here about message delivery being reliable as well. So you can imagine that these systems are built on a sort of stack of assumptions, right, that each have to build on one another. And we haven't even talked yet about how to implement reliable delivery. So that's something that we're going to talk about much more later on when we start to talk about failure more. All right, so that's it for today. Next time we're going to sketch out, or next time we're going to talk about this causal broadcast algorithm in more detail. And then we'll start to talk a little bit more about the total order anomaly that we talked about today, and why it is that it's that these sorts of mechanisms for ensuring causal delivery and so on don't ensure totally ordered delivery. See you next time.